In this video, we're going to work another example of a problem involving related rates. So the problem says that Main Street runs due north and south, and Park Avenue intersects Main Street at a right angle. So let's illustrate that with a diagram. Car A is on Park Avenue headed east at 25 miles per hour. Car B is on Main Street headed north at 30 miles per hour. At a particular moment, Car A was 0.8 miles west of the intersection. So Car A is right here, and it's headed in this direction. Car B was 0.6 miles north of the intersection and headed in this direction. We are asked to determine the rate at which the distance between the two cars is changing at that moment. Now, by the distance, we mean the straight line distance. So we're talking about that distance. Now, we're told that this angle is a right angle, so we have a right triangle. So we probably want to use the Pythagorean theorem, which relates these sides of this right triangle. So how about we call this distance B and this distance A. Then we can call that distance C. Alright, so the Pythagorean theorem says that A squared plus B squared equals C squared. And what else do we know? Well, we know that A is changing. Car A is headed east at 25 miles per hour. However, the distance A is shrinking. So that means that it's going to be negative 25 miles per hour. Car B is headed north, so this distance is increasing. That means dB is, the derivative of B with respect to t is positive, and it is what? 30 miles per hour. So we don't want to, we were given some distances, but we don't want to put those in yet because we need to differentiate before we put those distances in. Why do we need to do it that way? Because that distance A and that distance B are not fixed. They're not constants. They are changing. Alright, so let's differentiate both sides of this equation with respect to t. So we'll get 2a dA dt plus 2b dB dt equals 2c dC dt. I'm going to divide all three sides by 2 just to make this a little simpler. So what we're looking for is the rate at which c is changing, that's dc dt. The other variables we should have values for. Alright, so a is the distance that car A was from the intersection at a particular time, and that was 0.8. dA dt is negative 25. B at this particular instance is 0.6, and dB dt is 30. Now we need to figure out what C is. Well, B is 0.6, A is 0.8. We have the makings of a 3, 4, 5 right triangle. 0.6 is 3 times 0.2. 0.8 is 4 times 0.2. So that means that length C must be 5 times 0.2. In other words, 1 mile. Alright, so let's do some calculations. 0.8 times negative 25 is negative 20. 0.6 times 30 is 18. And then that's equal to dc dt. So dc dt is negative 2 miles per hour. The distance between the two cars is actually decreasing. Now we're asked to find the rate at which the angle between Park Avenue and the line segment passing through both cars is changing at that moment. So we're asked to find the rate at which theta is changing. Theta being the angle between the line segment of length C, the hypotenuse of the triangle, and the base of the triangle. So what we need is an equation that relates theta, well, probably to some of the lengths of the sides. How about we go with, how about we use the sine? The sine of theta is equal to the opposite over the hypotenuse, b over c. I think I'll write that as c times the sine of theta equals b. Because when we differentiate this, I think I'd rather use the product rule than the quotient rule. Alright, so neither c, b, nor theta is a constant, so we cannot substitute values in for those. Alright, so let's differentiate this with respect to t. We're going to use the product rule here, so c times the derivative of sine theta is going to be cosine theta d theta dt. Well, I don't think I have room here. In fact, I think I'm going to move this over here. So we've got c times cosine theta d theta dt. Now we need sine theta times dc dt is equal to dB dt. Alright, so we should know all of these except for d theta dt. Alright, c, as we were told before, or as we found out before, is 1. The cosine of theta is equal to the adjacent side over the hypotenuse. So that would be 0.8 over 1, 0.8. Notice we did not find the angle theta. That wasn't really necessary. We just need the cosine. We also need the sine. Well, the sine of theta is the opposite over the hypotenuse. That's 0.6 over 1. dc dt is the unknown. dc dt we found was negative 2. I left out d theta over dt. And dB dt is 30. I'm going to rewrite that so that it's legible. And let's see, that's going to be a negative 1.2 equals 30. So solving for d theta dt should be fairly simple at this stage. Add 1.2 to each side, 0.8 d theta dt equals 31.2. So that tells us that d theta dt is equal to 31.2 over 0.8, and I think that is 39. watts, radians per hour, which is sort of an odd unit of measurement. I suppose if you wanted to, you could turn that into degrees per minute or degrees per second or something like that.